we've seen how a secondary alcohol, or sorry, a secondary alkyl halide in this case the S isomer of 2-iodopentane can be converted into a racemic mixture of secondary alcohol. We use the squiggly line here to represent the fact that that's both a dashed wedge and a solid wedge, representing both the R and the S isomer. Simply by heating in the presence of water and undergoing a solvolysis reaction between the corresponding carbocation, which is planar, resulting in the loss of stereochemistry. And with the very weak nucleophile water, an SN2 pathway is not going to happen. It's going to undergo an SN1 pathway. And we've seen how we can do an SN2 reaction to generate the pure R isomer of 2-pentanol from the S isomer of 2-iodopentane by first treating it with potassium acetate in dimethylformamide to replace the iodide with the acetate with inversion of stereochemistry, producing the corresponding R acetate, followed by hydrolysis of that acetate with aqueous KOH, which is a nucleophilic acyl substitution occurring at carbonyl carbon. So we have a way of making a racemic mixture, and we have a way of making the pure R isomer. But what if we wanted, from the pure S isomer of 2-iodopentane, to create the pure S isomer of 2-pentanol? Is there a way that we can get net retention of stereochemistry? As opposed to net inversion of stereochemistry. If we're to maintain stereochemical integrity, we're going to need to do SN2 reactions, not SN1 reactions, because we know that as soon as we form a planar carbocation intermediate, we've lost the stereochemistry, and now there's no difference between attack from the top face or the bottom face of that MGP orbital. But we know that the SN2 reaction always goes with inversion of stereochemistry and is stereospecific. We don't know any reactions that directly yield net retention of stereochemistry in a single step. But we do know that if we have a quarter and George Washington's face is up, and we flip it over, and then flip it over again, George Washington's face will be up again. So if we were to invert the stereochemistry from S to R, and then invert it again in the second SN2 reaction from R to S, a double inversion would yield net retention. So two successive SN2 reactions will allow us to get net retention. We're not going to be able to do it from the S-iodo compound, though. What we're going to need in order to get net retention is either the S-bromo compound or the S-chloro compound. So let's change that system to start with S, 2-bromophenate. What we need in order to get a double inversion is we need something that is an excellent nucleophile to do the initial SN2 reaction, but is also an excellent leaving group, so it can be displaced by acetate ion in the second step. And the obvious choice is iodide. We know iodide is a very good nucleophile because it's polarizable and weakly solvated, and we know that iodide is an excellent leaving group because HI is one of the strongest acids there is. Therefore, the iodide is quite stable. The reaction conditions are quite specific. It's potassium iodide solid dissolved in acetone. The reaction is called Finkelstein reaction. And it is a way to convert alkyl bromides or alkyl chlorides into alkyl iodides, which is actually quite useful because we know that free radical halogenation reactions with iodine are endothermic. So we can't directly introduce an iodine into an alkyl chain by free radical iodination, but we can brominate or chlorinate and then use the Finkelstein reaction, potassium iodide and acetone, to do an SO2 reaction. And we know that acetone is one of the polar aprotic solvents, which means it will enhance the SN2 reaction. Because it's an SN2 reaction, it will invert the stereochemistry, and we will end up with the R isomer of 2-iodopentane. And it will work the same way on the chloride. We know that iodide is an excellent leaving group, and we know that iodine is an excellent nucleophile, but iodine is a better leaving group than is chloride. And chloride is a more strongly basic and better nucleophile than is iodide, unless you're in a protic solvent. Because the carbon-chlorine bond is stronger than the carbon-iodine bond, as is the carbon-bromine bond, we would expect this equilibrium to lie to the left towards the chloride or the bromide if it were allowed to proceed to reach equilibrium. The secret to our success is that potassium iodide is soluble in acetone. So we actually get the iodide ion in solution. Whereas potassium bromide and potassium chloride are insoluble in acetone and precipitate out, driving the reaction forward by Le Chatelier's principle by removal of a product as it forms. The reason for that is that the lattice energy for the smaller chloride and bromide ions in conjunction with potassium is significantly stronger. So the weaker lattice energy of potassium iodide is able to be overcome by the ion-dipole interactions between potassium and acetone solvent. We know that polar aprotic solvents solvate cations quite well, so that we will surround that potassium ion with the partial negative charges of the carbonyl oxygen. And that ion-dipole force is strong enough to overcome the relatively weak lattice energy with the large iodide ion with potassium. Potassium chloride and potassium bromide have a significantly stronger lattice energy because of the smaller size of the anion, and therefore the ion dipole force between the potassium ion and the acetone solvent is not sufficiently strong to overcome the lattice energy, and these two solids precipitate out. So it's very specific. It has to be potassium iodide because it has to be the potassium ion in order to make the ion or the lattice energy weak enough. Sodium iodide is not soluble in acetone because the lattice energy for sodium iodide is quite a bit stronger, and it needs to be acetone. It needs to be a polar aprotic solvent to enhance the SF2 reaction and also to strongly solvate the cation and produce that strong ion dipole force. Once we have the R2-iodopentane, then it's just a matter of doing the same two steps that we did to create the S2-pentanol, the R2-pentanol from the S2-iodopentane. So we would do the treatment with potassium acetate, PPMF, to generate the S isomer of the acetate. And then in the second step, we would treat this with aqueous KOH to hydrolyze the carbonyl oxygen bond, the S isomer of pentanol. So we now have ways of making pure R2-pentanol from pure S2-iodopentane, pure S2-pentanol from pure S2-bromopentane, or racemic R and S mixture of 2-pentanol from either the R2-iodopentane or the S2-iodopentane through simple hydrolysis in the presence of water and heat. Another question we might ask is, what if we want to make an ether with defined stereochemistry? What if the desired transformation were to start with S2-bromopentane and create from that either the R or the S isomer of 2-methoxypentane. And we could think in terms of making the pure S isomer, but we could also think in terms of making the pure R isomer. This is the kind of question that is quite common in organic chemistry. You have a starting material in hand, and you have a desired product, and you need to figure out what reagents will allow you to accomplish that transformation. The one on the right whereas the one on the left is a net retention stereochemistry. So we know that this will require two SF2 reactions. Whereas here, one SF2 reaction will suffice. We invert the stereochemistry once. We need to invert the stereochemistry a second time in order to get the net retention. That's the only way we know right now of how to get a net retention in stereochemistry. One could imagine simply trying to displace the bromide with the methoxide ion by treating this with sodium methoxide and methanol. But the problem with that is the secondary alkyl bromide is hindered enough to slow down the SN2 reaction without slowing down the corresponding E2 reaction. And so the major product we're going to get base is going to be the E2 elimination. It's just too strong a Bronsted-Lowry base to do a substitution reaction on anything that isn't either a methyl or a primary substrate. The alternative way to synthesize this methyl ether, if we work backwards, and an arrow like this, with the two lines on the arrowhead, is often used for what we call a retrosynthesis, working backwards from the product to a starting material. Successful if we have an alkoxide ion at an alkyl halide, in this case a methyl halide, no elimination is possible in the absence of beta hydrogens, and so we can get an SN2 reaction to go here, even though, so if we were to be able to make this alkoxide, we could accomplish the goal. And all we would need is to make sure we have the S isomer of the alcohol, or in this case, the R isomer of the alcohol. So working backwards, what we need is R to pentanol and iodide. If we could first convert this into the corresponding alkoxide ion and then do an SN2 substitution on the unhindered methyl halide, we could accomplish the goal. Well, we already know how to make either the R or the S alcohol. The only question to be addressed is how to convert the alcohol into the corresponding alkoxide. And there are a variety of ways by which that can be done. So if we want to have the R isomer of the product, or so the S isomer of the product will be S alcohol. And if we want to have the R isomer of the product, we'll need the R alcohol to start with. So how can we convert this into the corresponding secondary alkoxide ion? One way is simply to add sodium metal. Sodium metal, an alkali metal, gives up electrons very readily, and it will spontaneously give up electrons to the system to form H2 gas. And if we put coefficients of 2 in front of each of these, and put our counter ion in there, 2 hydrogens will come off to form H2 gas. The sodium will donate its electron to the oxygen to make an alkoxide ion at the same time as it becomes the sodium ion. We can develop that into half reactions by saying that sodium solid is going to give off an electron to become sodium plus, and at the same time, the alcohol is going to gain electrons to form the alkoxide and H2 gas. We're going to need 2 in front of there, and we'll have to multiply this reaction by 2 in order to get the number of electrons to add up. So we have a reduction, or sorry, an oxidation half reaction for sodium is being oxidized. And we have a reduction half reaction where the alcohol is being reduced. The alkoxide, or in essence, the hydrogen is being reduced from H plus to H0. The oxidation state on the hydrogen here is +1, and the oxidation state on the pure diatomic hydrogen is 0. So that's one way to do it. The alcohol can also be converted into the corresponding alkoxide ion by using a strong base something that's a significantly stronger base than the alkoxide itself. And logical choices are sodium hydride or lithium hydride, other alkali metal hydrides, or the corresponding amide ions. Those are two very common bases. These are essentially hydride ion and amide ion with an alkali metal counter ion. Both of these are good enough bases to take that proton off and generate the corresponding alkoxide ion. And in this case, the hydride ion, H2 gas, and in the case of the amide ion, NH3 gas. I've used sodium as the counter ion in all these cases. But it doesn't matter, you could use lithium or potassium. So an alkali metal hydride, an alkali metal amide, or just an alkali metal by itself are all ways that you can convert an alcohol into the corresponding alkoxide for use in the Williams ether synthesis. The equilibrium constant for these reactions are both very large positive numbers because the pKa of the alcohol hydrogen is approximately 15 and the pKa of hydrogen is 38 and the pKa of ammonia is around 35. So you're either 20 or 23 orders of magnitude less acidic with hydrogen or ammonia than you are with the alcohol, a much weaker acid on this side. The equilibrium constant can be obtained by the standard method that we used before for calculating equilibrium constants of these acid-base reactions by comparing the pKa of the acid to the pKa of the conjugate acid. And we will predict a constant of 1 times 10 to the 23rd, the difference between 38 and 15. And this one has an equilibrium constant of 1 times 10 to the 20th, the difference between 35 and 15. Both of these are effectively irreversible reactions that create the alkoxide and a gaseous product that bubbles out of the solution and is therefore not going to interfere with the purity from the product. Either of these alkoxide ions can now be reacted with your iodomethane, and the stereochemistry at the chiral center here is unaffected because the SN2 reaction is occurring at the methyl group to generate the product that we're after. In this case, right, the pure R isomer of the ethoxy compound, the methyl 2-pentyl ether, and in this case, the pure S isomer of the 2-methoxy pentane or